Hi, Jonas. Good
Hi,
afternoon
Ellie.
and good morning for those people in all parts of the world. Um, we have a lot of things to do today. I'm very rapid, as the title says. I have my coffee prepared, so I'm going to measure if it is possible uh, to design what you have promised in a coffee break. So let's see. Um, One thing before starting with the webinar today, I know there are some of you that are pro users of Frenetic AI, and this is a good moment, Jonas, to explain people that we are going to launch a big news in a few weeks with a important new feature in Frenetic AI. And this is worth it, and probably we are not sure yet, but probably can increase the pricing of Frenetic AI. So this big upgrade is the the planner design option. So that's why I would like to share today with everybody, and that's why I have copied a special code for you. It's only valid for this month in June. So this guaranteed that you are going to pay 50% of the pricing we have yet is 2,000 euros before the
100.
next launch. 200, sorry,
Yeah.
200 euros before the big launching. So this guaranteed that you are going to use the planner included in the pricing. And let me know if you have any question of this during the webinar. But now I don't want to give more time to you, Jonas.
Maybe also interesting, maybe Ellie, you correct me if I'm wrong, but everyone that registers gets a pro version has 1 week access to Frenetic Magnetic Simulator as well. So it can kind of also design magnetic components.
Yeah, now with the free license, because it's possible to try everything for free, it's 24 hours of free trial of Frenetic Magnetic Simulator. But the pro trial, we are giving 1 week, as you have said. And with this promo code, I would like to also include one free technical session with one of our engineers, so we can approach the use of the both tools to your current projects. So I think this
And we
is
also
a good.
have, if you're interested, we have also attractive pricings for the combination of the two tools, right? So I think,
Yeah, I think the best thing to try the tool is use the whole experience and try the both and see how it fits in your project. So I'm going to copy the discount for you, but it's going to be during the webinar in my screen. So you can start, Jonas, and I'm going to do silence.
Perfect. Yeah. Okay, welcome everyone. I will now present a little presentation first about LLC in general, and then we will show you how to use Frenetic AI to accelerate the design process. So let me share my screen. It's this one. Yeah. So you should all see now my slide deck. So the title of the presentation is Full-Bridge LLC in a coffee break. So let's see, I don't know how long you make coffee breaks, but I'm confident that we make a full design in around 5 to 10 minutes here live. But first, I would like to give you a very basic theory and also how one used to design LLC resonant converters, then a demo, and then we will have a bit time for Q&A. So maybe very general, what is a LLC? It's a resonant converter. You have here usually a full bridge or a half bridge. Now in our particular case, you have a full bridge here. Then you have the resonant tank, which consists of the resonant components, which are CL, and the magnetizing inductance of the transformer. And then on the outside, you have sometimes center tap configuration, or in this case, full wave rectification. The advantage of this topology is that it can be very efficient because you have zero voltage switching over a very broad output voltage range. And yeah, it's generally a topology that is more and more used. So if I take this a bit complex looking topology and simplify it, the whole input half full bridge on the left side is represented by a simple square wave voltage source, and the output by a equivalent or by a load resistance. Basically, you have the LLC, so the LLC tank and the output resistor. And what we usually do is we even simplified it more, and we do something that is called first harmonic approximation. So you just consider the first harmonic of your signal. So the input signal becomes a sinusoidal signal. Then you have the components, they remain unchanged, and the output is an equivalent resistor that represents the resistance the first harmonic sees. What I'm going to show you, I didn't invent myself. You see below here that the publication I took the liberty to take pictures from and also equations from. So that's basically a very nice paper that explains how you design LLC converters. So having this kind of circuit, you can calculate something that is called the gain function. When you think it's not super complicated what the gain function is, it's simply how the output voltage is linked to the input voltage. So and the nice thing is by changing the frequency, because of the frequency dependence impedances of these components, the output voltage will change. So basically it's just a voltage divider. You see here RE is always parallel to the magnetizing inductance, and then the sum of all in series. So this one again in parallel, and below the sum of the two impedances gives you this voltage divider, which is frequency dependent, as you can see here. Because we have a first harmonic approximation, a sinusoidal waveform, we can just represent X here, the reactance, as J omega L. So we have the parallel components here. They are also here parallel. It's basic circuit of a voltage divider that we are doing here. Now, what your job will be when you design an LLC converter is basically to pick the right L, the right LR and CR, so the magnetizing inductance and the resonance components, the inductance here and the capacitance here, the resonance components. Now, this is not super easy to do. You can imagine you have quite a lot of degree of freedom. That's why often one simplifies this equation a little bit by representing this like the frequency is always in relation to the resonance frequency I choose, after one chooses. The Ln is divided as the ratio between the magnetizing inductance and Lr, and the quality factor is given as here. And then this equation, I would say, simplifies like this, but still a bit complicated. Now, to be sure, the output voltage is not exactly just the input voltage multiplied by mg. You also have to take into account the turns ratio, which is another degree of freedom you have in your case. Now, what one usually does is build plots that are a function of Fn and Qe. So for different Ln's, so the ratio between magnetizing inductance and the resonance inductance, and for different Q, so quality factors, you get different plots which are a function of the frequency here. So you can think of, if you are your operating point, let's say you chose Ln like this and Qe like this, and your operating point is one point on this plot. By changing the frequency back to lower values, you actually increase the gain. By going up, decrease the gain. So this is the very basic fundamental concept of an LLC converter, and most of the resonance converters can be discussed in the same way. Now, your approach is you have to think, what are your input requirements? So you have to get then from these requirements the turns ratio, the minimum gain you need from the resonant tank, the maximum gain you need from the resonant tank. And then you choose, often this is done graphically, from all these plots, an ln and q that ensures converter reaches the required gain over the frequency range from f minimum, the minimum frequency you allow, to the maximum frequency you allow. You have to think you have the resonance frequency. This is the point here, 1. But then to control the output voltage, this is done by changing the frequency, the input frequency, basically the full bridge switching at the beginning. Now, when you have this, you go back, calculate LR, CR, and the magnetizing inductance. And then you basically finish the circuit design, right? You know then here the different circuit elements, how they should be, but you also have to then select and design components. For instance, the LLC transformer, which is challenging, one of the challenging tasks. So basically that is the approach how you do this. Now, I guess you need a few hours to do this, if not days. And I would like to show you now how in Frenetic AI we can do this in the time of a coffee break, basically. So I just started Frenetic AI, and all of you have access to this. You just register, and you will get a trial license for that. And if you register, you also get access to Frenetic magnetic simulator, something I will also show today quickly. So what you do first, you select your topology you're interested in. And now I picked a case. Now there you have, of course, more free. You can choose whatever your purpose is. But let's say you want to have an input voltage of 300 to 400 volt and an output voltage of 48 volt. You can also have here a range, but I will not do this here just for saving a bit of time. And let's say in my case, I have 600 watt output. And then I click design. And now the tool basically is going through these steps for me and is analyzing a nice combination of LC and LMs, LR, CR, and LMs. So I can work with which I can work. This could be a typical application of that, could be a server, like a server for server farms. Let's say you have often an intermediate voltage of 48 volt, and the input could be from AC to DC rectifier first, depending whether you're in the US or in Europe. You have here input voltage in this range. The output power can be, of course, higher, but this is just an example here. Now I would say at the moment when I clicked here, which was, I don't know, maybe a minute ago, that would be the time to go back to your coffee machine and wait maybe a few seconds, or that's the moment you actually drink your coffee. In parallel, because I would like to show you later, I already, and this doesn't work now because it's running, I made a design before the seminar here with a resonance frequency of 300 kilohertz. I would like to show you how you can compare different input or design criteria, parameters, and like this get your optimal design for your purposes. Okay, let's wait a bit. It's not a very simple task, so it takes a bit of time to get through all these degrees of freedom that are available.
I think a lot of people is using at this moment at the same time.
Yeah, that's
we are having a lot of registrations these days.
Yes. Yeah, who knows?
Or maybe it's your Wi-Fi.
It's happening in the background, right? So should not be my Wi-Fi. But yeah, I expected this, but I guess I promised in a time of a coffee break and not in a microsecond, right? So
we'll do in a coffee break. Less than 30 minutes.
Let me show you in parallel something else. That's what I showed before. So I already made a design before the webinar where I put exactly the same inputs in, and the resonance frequency was I I set to 300 kilohertz because I wanted to enforce a resonance frequency. And you can see then here the different components, like for instance, basically the output was the capacitance here, the magnetic spectral resonance inductor here, and the magnetizing inductance that I need here, and also the turns ratio for this particular case. What I then did, basically this is my circuit design. Let me check here now. In the meantime, this is finished. You see here now, I didn't set any resonance frequency. So the tool proposes a resonance frequency of 100 kilohertz, which is reasonable, but doesn't have to be the exact thing you need. And you have the components as I just showed before. So basically you did your circuit design. Now what you can do now is, which I will not do today, you can generate a circuit simulation file. In this case, it's LT-SPICE, but I think until end of week, we also add Plex. So you will also be able to download Plex files here. So just click this button and then it runs and designs a Plex file for you. And you can do the simulation in more detail if you want. Another thing we can do is going to design a magnetic. So basically I click now this step. Basically it's a select design components such as, for instance, LLC transformer. So if you design an LLC transformers, you have two degrees, you have a lot of the degrees of freedom, but you have two distinguished different ways of doing this. One is integrating, using the leakage inductance as your resonance inductor. So don't have an external inductor, or have a separate inductor here and try to optimize your magnetic component. Now, in our case, what it proposes is a magnetic component with an integrated inductor. It does this by default. But if you can't find a solution, then it will provide two outputs here, the resonance inductor separate plus the LSC transformer. So now basically you have all information, and I think now it's the time to stop the timer. I don't know how long it took, but this was your coffee break, because now you finished your design of an LSC converter. What you can do is, if you want to understand everything a bit better, you go to the magnetic simulator. So you transition to another tool, and in this tool, you can now continue working. You get much more information about the design that has been done regarding winding, cores, and also the waveforms. Another thing maybe you are interested in, you see here the switching frequency for the case 400 to 48 kilovolts. So that was one operating point, but what you can do, as I said, you had 300 to 400. You can also go add an operating point. So basically the first one was 400 volt. Let's run this first. And the second one is 300 volt. So we have the two corner points now. Now this is the second operating point. And you see here it goes down to 60 kilohertz. So it reduces the switching frequency because it needs a higher gain. And you can also here have a summary of all the results. So you see, for instance, how the losses compared. Let's see, I think it didn't yet consider both operating points. But you can see now, how the winding losses, the total losses, or the core losses change with regard of when you change the operating point. And also, if you go back to the simulation, you can change your switching frequency here to simulate, let's say in Plex or in whatever LT-SPICE, then another operating point. I will not discuss this tool in details, but basically you're ready here now to order. You have here a bill of material. You know exactly which core, coil former, and so forth, leads, wires, and so forth you need. So basically you're ready to produce this design. As I said, as Ellie said, if you would now register for Pro version, we give you a more detailed tour through this product here. Now, in this case, maybe I would like to try compare different designs. So what I can do is just start a new project. I can also delete, rename projects, do a new design as I have done here. Then you can compare different outputs, like for instance, different magnetic proposals for different input requirements. Okay, I think that was it. Quick explanation of how you design an LLC converter, and you not need to understand all these things in the future anymore. But I'm happy to answer now
have
questions
my
if you have.
coffee.
The
Not
coffee
finished
not yet,
yet.
right? Not finished. Okay.
Yeah, Jonas, could you show again how to move from Frenetic AI to magnetic simulator? Because I have some users that recently have asked about, I don't know
Yes.
how to change to magnetic simulator. It's very easy because the button is in the top right corner, but just
so
in
basically,
case.
if the tool has certain options, but the buttons to transition to other tools is all up here on the right. And if you click the magnetic simulator, it opens it. Now, if you don't have access to it, it will pop. Another window will show up. But if you have access to it, it will look like this. Yeah. So basically, one click.
Okay. Is there any questions for Jonas regarding the technical webinar? You can use the chat or the questions and answer space. Okay, we have.
I just saw a comment here. Just the feedback, a progress bar would be nice, and I fully agree on that. We fully agree on that. It will be released in the next. Well, we actually hoped it will be released already today, but it will be released in the coming days when also the Plex feature will be released.
Okay, we have 2 more questions.
Yeah, one is, do you have to be online to do a design? Yes, it's all cloud-based. So basically, it's not, you don't install anything. You don't have to worry about software installation. It's all cloud-based. You log in and then you do the work. Maybe interesting in this regard is also if you're in the, let's say you're here and maybe one thing I forgot to say, in this tool, you can also say, I don't want the integrated inductor. And ask the tool to suggest you. Here you have more flexibility to actually do changes. And you can also do changes here manually. You can change the core, and you can also optimize and find the right trade-off for your purposes. But what I wanted to say, you can also share your design with your colleague. So if you're in a company where many people work, you can easily add you save it and then share it with your colleague, and he or she can continue working on it. So what is the optimization goal, volume, efficiency, cost, or compromise? So it's kind of a bit of a compromise, but our standard algorithm is optimizing for volume. So basically what it does is trying to make it as compact as possible, but not overheating it. Now, if you want to have a more efficient design, what you can do is also here change the temperature or magnetic, or I can say something like maximum magnetic temperature equals, I don't know, 80 degrees. Then it also you have a bit of freedom in this tool. In this tool, you have more degree of freedom, and you can optimize according to your needs. Then for calculating the losses of the transformers, how is this calculated? Use equations or FEM. So this is a very good question. It's also a very complicated question to answer because we have lots. Let me close the screen. We have a lot of different models in the background, like we have winding loss models that are semi-analytical, analytical. We have core loss models that are empirical. We have, depending on what we are modeling, different models, but so far we are not using FEM just because we need very fast design, like it has to be very fast, so we have to compare different designs. We are thinking including a FEM solver in the future, in the sense like if you have your first design, final design, you click this button and you get a bit more accurate design. But generally, we are very happy with the accuracy. And also very open. We have our fact sheets, and if you have questions about accuracy, you reach out to us, and we are happy to discuss this and show you what we can achieve. How can we get job opportunities? Not sure.
This is something that we need to ask
Frenetic.
to HR. It's not here in the webinar today.
We cannot.
But okay.
How can this tool be used only for the transformer design? I suppose the LLC design is already done. Well, this is a good question. I can show you this. We have to look a bit at the time. But if you know all this CR, LR, so everything you know already here. Basically, this is not the Frenetic AI is not the right tool. You need this tool here, because here, so in the Frenetic magnetic simulator, you can put in all these parameters you just said, and then design the magnetic for you. So what are you asking here? How can this tool be used? It was not shared before. What I was saying is, this tool is Frenetic AI is here to find you the right CR, LR, LM, and so forth. So if you know everything and are only interested in a magnetic component, then actually you need this tool, Frenetic Magnetic Simulator, and you go to this input mask here. You put in FRLR, and there's a resonance frequency here, and then it does the calculation. Then it limits it. It's here to design you the magnetic component only. I hope I answered the question correctly or understandably. Yeah, what are other converters? Well, at the moment, but we are adding converters. We have these ones, but the best thing is we also working now on CLLC. We are working on other topologies as well, like center tap, LLC with center tap, and so forth. But the best thing is you just register and try the tools out, and then you know. I don't know about PDF or PPT of this presentation. Ali has to answer this question.
Yeah, we can say if you are agree, Jonas, to everybody with the recording in the following days.
Yeah, that's fine. Yes.
We have a couple of minutes for the last question. I think.
Yeah, we have to be. There are many more questions.
The last question is very interesting. It's regarding AI model.
Yeah, there are two. One question is, how high is the agreement between the simulated temperature and the sample of the magnetics? I just want to answer this because we have a thermal fact sheet where we show measurements we did in the lab. So yeah, reach out to Ellie and she can send it to you. Okay. Or maybe it's online, I don't know. It should be. It was published at some point.
Is the thermal model of Frenetic?
Yeah, we have a fact sheet.
Yeah, we have published in our website. Let me find the link for you. I'm going to include in the email with the recording, but I'm going to share. Okay. I think so this one.
Yeah, perfect. Yeah, exactly. So let's do two more answers. One is the AI. And then one other question. So does the term AI in this context mean that you have a database of designs that you chose from, or do you rather use some sort of genetic algorithm for the optimization? Well, AI means we use latest AI models to help us, but they are not just, we augment them with our knowledge. So with equations and so forth, but it's not a database. It's not at all a database. And then are you able to produce prototypes? Yes, we have actually. Some clients have. If you are customer of Frenetic Magnetic Simulator, we offer also the production of samples for you. That depends on the contract, but you have a certain amount of samples per year. So you basically, I can also very quickly show this. You go here, order magnetics, and we will ship this for you. Yeah, I think we have to stop here, but I think there are also no more questions. Maybe I missed one of the questions. Sorry for that. No, not intentionally. It's just send me an email and I will answer any question.
Yeah, I have shared my email just in case you need to contact me regarding Frenetic AI, questions about pricing, discounts, or questions for Jonas. I can forward to him. So I think, yeah, we are going to finish this session, and I hope you can join next session. Because we have a very good surprise with us. Next week is going to be here Sam Ben Jakov again, so you will receive the invitation.
Very nice.
Good. Thank you, Jonas.
Thanks everyone for listening.
Bye bye. Thank you, everyone.
Bye bye.